So welcome back to our seminar today. Max is joining us again to talk about, subconstituents of triangle-free Drackns.
Thanks, Maria. And thank you to Sabrina for scheduling me and encouraging me to give this talk. Yeah, it's great to be back. I wish I'd been here more last term. Last term I was teaching at this time, so I couldn't come. This last month I've sort of just fallen into a schedule that doesn't allow it. Hopefully I'll get back here more. It's good to be back. Yes, and so I should say I'm now at Simon Fraser, but I mentioned being back. I did my PhD at Waterloo with Chris, and this is work that is part of my PhD, something I did sort of at the tail end of it. And I will talk. Yeah, let's leave it at that for the start, and then let's just get to it. So I want to talk about these subconstituents of triangle-free Drackns, and there's a lot of words there that need to be defined. So we'll start with subconstituents. And so the idea is that for a vertex in a graph, it could be any graph, but usually we'll be thinking about a distance regular graph in this talk, which I will define in a bit. The kth subconstituent is, or the kth subconstituents are the graphs defined by all vertices at distance k from some fixed vertex. And so for an example, the sixth cycle is a second subconstituent of the Peterson graph. I can take a vertex in the Peterson graph, and I can take all of its neighbors, and then its second neighborhood is going to end up being the remaining vertices. This one has those two vertices as neighbors. This one has these two, and this one has these two. And we find that if you look at the vertex, the graph induced on those red vertices, you get a sixth cycle. And that would have been true no matter which vertex I picked to start. It's not something guaranteed in this definition of subconstituents, but it is true in this case that any second subconstituent in the Peterson graph is a sixth cycle. Now, this, just to give another example that sort of motivates some more interest in these things, is that the Peterson graph itself is a second subconstituent of another distance regular graph. What you can do is you can define this Klebsch graph by taking an independent set in the Peterson graph of size 4 and building a new vertex and sort of attaching each vertex from that independent set. And then you do that process over sort of by rotating cyclically. I can find another independent set here. And actually there are 5 independent sets of size 4 that I can pick. And for each of those, I build a new vertex and attach it to the independent set. And then I build one more vertex, which I attach to the 5 independent sets I just created, or to the 5 vertices attached to independent sets I just created. And then from this vertex, its neighborhood is these 5 new vertices I just created. I only drew 2 of them. But then the second neighborhood is that Peterson graph. And here again, also, actually, yeah, it's true that all the second subconstituents of that Klebsch graph are going to be these Peterson graphs. Okay, let me erase my slightly messy picture there. And I'll just say, continuing on in the same vein, actually, the Klebsch graph sits as the second subconstituent of another strongly regular graph, which is this collinearity graph of the generalized quadrangle 2-4. That one I won't draw, but there are nice pictures where you can sort of see a Klebsch graph hiding in there. So already we have this sort of interesting continued structure in a family of graphs. The neighborhoods, or in this case, the second neighborhoods, contain something very, very nice and beautiful. And this procedure, I mean, you can ask, well, I've gone this far. Can I go further? Can I find another distance regular graph that contains this thing as a second subconstituent? And actually, you can. And that's going to sort of start the motivation for what I'm talking about today. More generally, what you can do is you can note that this generalized quadrangle graph, it's a strongly regular graph with these parameters. So these are the number of vertices. This is the valency. This is the number of triangles on a vertex, and I won't write it. And this is the number of common neighbors of a pair of non-adjacent vertices. And anytime you have a strongly regular graph with these parameters, in particular, where this parameter, the c value, is exactly half of the k value, your graph is a first and second subconstituent of a certain distance regular graph of diameter 3, which is known as a drackn. And the sort of way you construct that, and I'll show you with a different example where it's a much smaller example where the distance regular, where the graph in question is the 5 cycle. So let me just pull out a marker. So I have a 5 cycle here, sort of embedded in a complete graph on 6 vertices, which is a strongly regular graph 5, 2, 0, 1. And so the way you sort of take a strongly regular graph with these parameters and find some diameter 3 distance regular graph containing it is you embed it in a complete graph like this, where you sort of you put it in, and then there's these other edges, and then you double everything up. You say, okay, well, this vertex here, I'm going to replace it with a vertex 0 and a vertex 6. And this one can be 1 and 7. This can be 2 and 8, 3 and 9, 4 and 10, 5 and 11. And then you go over here and you do this sort of doubling process, where so now what I've done is I use all the edges that weren't part of the distance regular graph, or the strongly regular graph. And I just say, okay, in those cases, I just double up the edges, sort of putting the low numbers to the low numbers. So for instance, here, this vertex, if that's the 0 vertex, then 0 gets it's adjacent to the 1, the 2, the 3, the 4, and the 5. But anywhere that I did have an edge of my distance regular graph, now I get a twist. So for instance, there's none that's easy to draw here because so for the 8 and the 2, 8 and the 4, 10, there, because I had an edge of my 5 cycle, I twist. And that twist in 5 cycle is going to correspond to this long cycle in there. I might have missed an edge or two. But anyway, that's a procedure that gets you from this distance, from this complete graph up to this larger graph, and it's covering construction. And I'll now give some more definitions about what I'm talking about these drackns in general. So what I just explained is an example of a distance regular antipodal cover of a complete graph, namely the icosahedron being 1, or there being one whose second subconstituent is this GQ24. But now let me describe drackns a little more generally, because what I want to talk about is subconstituents of drackns in a more general case. Sort of the motivation being we have this result. I didn't state it as a result, but this fact that these second subconstituents of these particular kind of drackns are particularly nice. They're strongly regular graphs. So the question is, okay, if I look at this more general family of these graphs called drackns, what can I say about their second subconstituents? We'll say something algebraic. It won't quite translate into something about a distance regular graph because of diameter concerns, but we'll still get an algebraic characterization of what's going on in these neighborhoods using standard tools for doing so in distance regular graphs. Okay, so that was the sort of intro. Any questions before I go on? Okay, that wasn't very long. Let me try again. Any questions before I go on? Okay. So drackns. So what is a drackn? I've said this word several times. Not really a word, but it's a pretty good acronym. So a drackn is a distance regular antipodal cover of the complete graph. There's where that KN comes in. I believe this terminology is due to Chris. So I should define all these pieces of what I'm talking about now. And in order to do so, I'm going to start with the easier ones to define, which are the latter ones, and then we'll move back to distance regular. Working with this stuff, you always kind of end up having to define distance regular. It's never that much fun, but we'll go through it. We'll get it. So what do I mean by antipodal? Well, a graph of diameter d is antipodal if this relation of being at distance d or 0 is an equivalence relation. Now, another way to say that, which is more confusing linguistically, but I think clear, is that if a vertex is at distance d from another vertex, then those two vertices are at distance d from the same vertices. And I mean, that's what's encapsulated by this equivalence relation. Plus, in order to be an equivalence relation, you need to be related to yourself as well. That's why you add that 0 in there. Another way to think about this, if you're already comfortable with distance regular graphs and distance matrices, is that the distance matrix AD, which records when two things are distance d, that matrix or that graph, the associated graph, is just going to be a bunch of complete graphs. So the things clump up in the distance d, you get all these complete graphs. That's a way to think about what this antipodal means. Okay, now let me describe what it means to be a cover. So to be a cover, so graph X is covering a graph Y if there's a graph homomorphism from X to Y, which maps the neighborhood of each vertex in X bijectively onto the neighborhood. Yeah, it maps V bijectively onto the neighborhood of the image. So what that means is it's a special kind of graph homomorphism with some extra property. Usually I give an example here. I mean, we already had one example of the icosahedron covering the complete graph. Let me describe it. Let me describe specifically what it means to be a cover of the complete graph, because that's the sort of specific case we need. And I'll go specifically to a connected cover of the complete graph. It's a little bit easier to think about. So here the idea is just that we have this homomorphism in the complete graph, also known as a proper coloring. And that proper coloring has some extra property, which is that each vertex of color I, color 1, say, it has a neighbor of exactly each other color. That's what this bijective onto the neighborhood property is telling us. So for instance, some cover of K5 might look like it's a vertex 1, and it's got a neighbor 4, a neighbor 5, a neighbor 3, and a neighbor 2. Funny looking 2. And the 5 there, the 5, maybe it sees that 3, but maybe it sees some other 4, some other 1, and some other 2. I'm at 1, oh, that better see a 4 and a 2 and also a 3, and something like that. This process must close if we're talking about a finite cover. I don't think I said finite anywhere here, but I am restricting to finite graphs. But so if this sort of property holds, then you're a cover of the complete graph specifically. Now, if you want to be a cover of some other graph, you take these things and you sort of remove some of these pairs of edges for the edges you don't have in your graph. But that's neither here nor there. Okay, and the other point to make about this thing is when we're connected, if the graph is connected, then the color classes, they all are the same size. And this we call the index of the color, of the cover. Or we say it's an R-fold cover. We use R to denote this index, and that'll come up quite a bit. So the icosahedron I saw before, that was a 2-fold cover. Okay, let's go on now to distance regularity, and then I'll show a few more examples, and then I'll pause to ask for questions after that, get some clarification. Okay, so the most salient definition of distance regularity for us is going to be this one where you build a distance partition. So you pick a vertex in your you pick a vertex in your graph, and you look at the neighborhoods so you look at your vertex here, and you look at all of its neighbors, and then you put all the vertices at distance 2 from your starting vertex in this next blob, and at distance 3 in the next blob, and maybe you go on, but for our sake, we don't need this. And also because we're working in diameter 3, we're not going to need more blobs. And then once you've done this, there's a property that may or may not hold, and if it holds, your graph is going to be distance regular, or at least it's going to be pretty close to distance regular. There's a little bit more to do. And that property is that you have this well-defined intersection array, which tells you about the number of neighbors of the various vertices. And so I mean, I haven't written down specifically, but what is B0? B0 is the number of vertices that this vertex is adjacent to, also known as the valency, because this is the vertex itself. It's in this partition B0. B1, let me just go to here. B1 is if I pick a vertex here, how many neighbors does it have forward into the next part? Whereas C1 is how many neighbors does a vertex here have backwards? Similarly, C2 would be if I have a vertex here, how many neighbors does it have backwards? B2 would be how many does it have forwards? I think that's why I wrote that forward there for B2, or for B1 rather. You always look at the vertex here. If you're in the part of 2, then this is where B2 and C2 are defined, going either back or forward. And then, of course, there's also this A2, number of neighbors that a vertex in the middle neighbor has, going to its own part. But this independent of the chosen vertex property, which is something I'll mention in a second, means we don't actually need to think about these numbers in here when we're defining the intersection array. Okay, and so what is my claim? My claim is that the graph is distance regular, or my definition is that the graph is distance regular if I have this partition defined, or if I have this array defined, given this vertex I picked to start with, and that array is actually the same no matter what vertex I chose. And one particular consequence of that is that this B0 notion is the same no matter what I chose, which means that the graph is B0 regular. So since the graph is B0 regular, that means each vertex has valency B0. And so in particular, the number of neighbors in here is going to be B0 minus the number of back neighbors and the number of forward neighbors. So this number of neighbors inside of a part doesn't actually need to be defined if I have this data, which is why you leave it out. But that would be A0, A1. A0 would be 0, A1 would be the number of neighbors in here, A2 would be the number of neighbors in here, and so on. And that A is coming up here in this fact, which is sort of why in algebraic graph theory we care so much about these matrices or graphs with this property, is that it gives us this very nice algebraic way to work with the matrix. So A1 is the regular adjacency matrix graph. AI is this height distance matrix, which I already mentioned. And the very nice thing you have in a distance regular graph is this 3-term recurrence, which tells you that if I want to understand the product of these matrices, all I have to do is look at the sort of things back than the things forward. So if I know these matrices, I can get everything I want. And in particular, this means that the algebra generated by the adjacency matrix is going to be very nice. It's going to be very low dimension. All right, and we'll use this fact later on. All right, so that's distance regular, and so if I have this additional property, I'm happy. Now, I went through this because I do need this later on. I need this sort of general fact about distance regular graphs, but in the context of having an antipodal cover, I can actually do something much simpler. I don't need to define all of these numbers just to get the intersection array of a distance regular antipodal cover of the complete graph. It suffices to just look at this number C2. That's all that really needs to be defined. And we can get everything else in terms of that. And let me show you that on a few examples. Or well, let me show you C2 on a few examples. So here's some examples of Drackns that I haven't mentioned yet. I also mentioned before, I mentioned the icosahedron covering K6. Here's the cube covering K4. Here it is. It's drawn in a way where you see there's the cube, and I've sort of colored the vertices according to this projection. So you imagine the yellow vertices getting mapped onto the yellow vertices, and that's sort of shown as an intermediate step here, just to get a little more clarity of how I imagine these things folding in on themselves. And that's a pretty natural way to do it. And it's the inverse of that process where I said, okay, well, if things are if I had a purple edge here, then I cross the matching when I jump back up. So this is one example, is the cube, Q3 covering K4. Another example that we can think about is the line graph of the Peterson graph covering K5. So here's the Peterson graph. We saw it already before. What let's take its line graph, and what you can notice in the line graph, you can notice it in either picture, is that we have these independent sets corresponding to the colored edge, the coloring I've given. And each of those independent sets, or each vertex, say each yellow vertex, it's an incident with one orange, blue, purple, and green vertex, and one edge of each other color. So what that means is that the homomorphism given by this coloring onto K5 is actually a covering projection. So this graph the line graph of the Peterson graph is distance regular, it is a distance regular cover list. And this is our first example where the index, or that R value, or the size of the color classes, is greater than 2, which is really where we want to be working, because sort of most everything I shouldn't say everything, but the R equal 2 case is pretty classical. It's worked out mostly by Seidel and Taylor in the 70s. Well, there's other people too, but the survey of Seidel and Taylor would be the place to start. 70s, 80s. Anyway, so that means we're sort of more interested now in going to these higher index cases. That's what I was thinking about, and it's where we're headed. And this is our first example of a higher index case. All right, so there's some examples, and then the other thing I want to say about them is that we actually can work out that this is the intersection array we get for a drackn. Notice that it only depends on the index, the size of the complete graph we're covering, and this parameter C2. So in all of these examples, we have this number C2, which is the number of, which is this sort of, in my general picture, it was this number of back neighbors from distance 2. That's all we need to pay attention to. And in a cover, C2 has this, in the cover of a complete graph, C2 has this interpretation as number of common neighbors of 2 non-adjacent vertices from different fibers. I don't know if I defined fiber, but fiber is color class. So in particular, so if I look at 2 non-adjacent vertices here, they have 2 common neighbors, so that C2 value is 2, and that's, you can check that's going to be the same for all of them, but that's sort of what it means. This is distance regular. If I look at 2 non-adjacent vertices here, so I didn't mention the 6 cycle, but the 6 cycle folds back up onto K3, onto a triangle, so that's also a distance regular cover. They have 1 common neighbor. So this one, so now if we use this notation to describe the parameters, what we see is that this is a 3, 2, 1 cover. It's a 2-fold cover of K3, in which any pair of non-adjacent vertices from different fibers have 1 common neighbor. This one is a 2-fold cover of K4. That's this 4 and this 2. Where non-adjacent vertices from different fibers have 2 common neighbors. So that's C2. This one is a cover of K5. Its index is 3. The size of the cover class is 3. And I believe it's 1. Any pair of non-adjacent vertices from different colors. So for instance, I pick this yellow vertex. I pick this yellow vertex and some purple vertex that's not adjacent. And in fact, yes, they have this 1 common. Yes, so it's 1. And this one is a 6, 2, not adjacent. 2, I think. Maybe we can double check. Maybe I should leave this as an exercise. Non-adjacent vertices, different fibers. Just 1. Just 1. Okay. Okay, so that's the parameters of the drackn. Let me pause here for a second and see if there are any questions, because that was a lot of definition we just went through. All right. So I mentioned the algebras of these distance regular graphs being very nice. One of the very nice things that we often do is we use these algebras to calculate the eigenvalues. And of course, in this particular case, we can do that. And we can use these parameters to calculate the eigenvalues of the distance regular cover. And in much the same way you've seen derivations of the eigenvalues of the strongly regular graph. I suppose if you don't know strongly regular graphs, I can now very easily define them because they're exactly the distance regular graphs of diameter 2. So if you're familiar with the strongly regular graphs, you've just met a generalization thereof. And we probably all seen the derivation of the eigenvalues of a strongly regular graph, the eigenvalues of a distance regular graph. of diameter 3, in particular one of these antipodal covers, goes along the same lines, and you get out something pretty similar. What you get is these expressions for the eigenvalues, which will be important towards the end, but don't need to be. We don't need to focus on them too much. It's a standard calculation, and I think it's there's more interesting things to focus on. We will come back to them at the very end, and I'll say, hey, remember that slide that I didn't spend enough time for you to look at? Well, now it matters. But for right now, just the knowledge that we can calculate these things explicitly is probably good enough. Okay. Yeah, we want to talk about techniques for calculating sort of the eigenvalues in the second neighborhood, which are going to be related to these ones, and actually include these with different multiplicities, with lower multiplicities. But there's some other stuff going on as well, which is what I'd like to talk about. Okay. Now, I mentioned right at the start that I want to just restrict specifically to triangle-free Drackns. So these would be ones with A1 equals 0, or if it's other characterizations. But yeah, if there's no triangles in Drackn, then we were restricting to some very special sub-examples. Now, of index 2, there's just a few examples. There's just the complete graphs minus a matching. Those give examples of triangle-free Drackns. There's a very, very special family of examples that come from more graphs. Gardner did a lot of the work on these distance regular antipodal covers in the 70s, maybe 80s too. So if I have a more graph of girth 5, I get a Drackn. I'll mention a little bit more about that in a second. And in particular, I get the Drackn as a second subconstituent of a more graph. So here's subconstituents playing a role again in this nice characterization. And then if you think about triangle-free strongly regular graphs, there are actually very few examples. We only know of 7 specific graphs. The setting is a little bit different here. When we're bumping the diameter up by 1, we're now at a diameter 4. We're looking at, diameter 3 distance regular graphs, and we're restricting specifically to a subclass of them. These ones that are antipodal covers, but it's not a terrible restriction. In some broad sense, it's about a third of them. Not a numerical sense, but there's a way to split them into 3 classes, one of which being these antipodal ones. And among these, actually, there is this infinite family known. And I'll mention that construction as well in a second. So if I start proving things about these triangle-free Drackns, at least I know I'm proving something about infinitely many graphs, which is nice. I mean, the hope would be that there's more, right? The hope would be that there's more examples here, and that would be very interesting. But this is what we have so far. Okay, so I'll go on from there. Let me say just a little bit more about this Moore graph. I mean, you could define a Moore graph as such. There's a lot of different definitions of Moore graph. Some of them give exactly this. Some of them give broader classes of graphs. But in particular, when I'm talking about Moore graphs here for the context of Gardner, this result is just saying that if I have the phi cycle, the Peterson graph, the Hoffman-Singleton graph, or the putative graphs on 3,250 vertices, then their second subconstituents are Drackns with these parameters. I mean, the 5 cycle doesn't give you anything. The Peterson graph gives you the 6 cycle as a second subconstituent. That's what I started with. There's this very interesting graph, the second subconstituent of the Hoffman-Singleton graph, which is a Drackn, and perhaps there's more here as well. So that'd be very. I mean, it sort of relates this back to the search for more graphs, which is both interesting and make you think, whoa, okay, but this particular subproblem maybe not workable. Or maybe you're more optimistic and you feel like it is workable. That'd be great too. Okay, so that's the sort of very specific examples, and then there's this infinite family. I don't want to spend too much time on this construction, but I'll just mention it so you know sort of what we're talking about. The way you can build this infinite family, this was done by Ken Morehouse, I think in 1995. And what they did is they worked with some large power of 2, and they took the finite field over that power of 2, or applied that power of 2, and then they took 2 copies of that, and then one other extra bit of information in GF2, and then they defined an adjacency relation on tuples from that set by this sort of wild-looking thing. Tuples with fixed A, so I'm fixing an A and I here and letting alpha vary. These are the color classes. So you get colors according to this. You get 2t colors, and the size of these coming from the different choices of A and I, and you get that the size of each of these color classes is 2 to the 2t minus 1. Right? And then you have to, obviously, all the work is in checking the adjacencies, figuring out what these things are.
Read what you were doing with those VAIs, because I think the connection froze for half a minute.
Sorry. Yeah. Am I back? You can.
Now you're back.
Yes. Yeah. Okay. So I was just saying that these define the fibers or the color classes. So this set gives the color classes in this cover. I was just saying that to give some more context for the result. Okay. All right. So that's my sort of background on Drackns. Now I want to get into thinking about the algebras of these subconstituents via Terwilliger algebras. Any questions before I go on? Okay. So moving on. So the basic idea of the Terwilliger algebra in general is that I have this algebra of the adjacency matrix, and then I sort of introduce also some projections onto the parts of the algebra that are indexed by the subconstituents, all the various subconstituents. And I'm specifically working in a distance regular graph, so you can have in your mind that picture before of, oops. I've got all these different pieces. Let me just resize here. And so I'm sort of introducing these EI, which are projections onto these parts. And that's chopping up my algebra into these smaller pieces. And you could study that algebra. This is what Terwilliger defined. And just a very brief piece of history. There's been a lot of work done on this in a lot of directions, but just in terms of the sort of the little bit of the branch of the history that goes into what I'm talking about is that there was this introduction of these objects by Terwilliger in 92. And he worked out explicitly what's going on with a whole bunch of families of examples of large diameter. And then a few years later, Tomiyama and Yamazaki, they studied the strongly regular graph case and worked with that. You get sort of worked out exactly what's happening there with subconstituents of the strongly regular graphs. And then a student, Hamid Shirazi of Chris's, in his PhD, worked out sort of what's going on in general for Drackns. And that, he worked out sort of the algebraic properties of this Terwilliger algebra, the size of the irreducible modules, and a little bit more information about them. And then using his techniques, what I did is I said, okay, well, what can I do explicitly to calculate specifically the eigenvalues in the triangle free case, which goes beyond, it requires sort of partitioning things up a bit more based on this extra information we have in the triangle free case from what Shirazi did, but is definitely inspired by what he did. And the first sort of breaking things down into row and column partition is the setup that he used, which is sort of all part of this lineage of these Terwilliger algebras. So I'm not going to talk explicitly about the properties of the Terwilliger algebra. See Hamid's thesis for that, but I'm very much using those ideas and using the decomposition of the Terwilliger algebra to get the block decomposition I'm about to show you. Okay, and so what is the result I actually did? What did I do? I showed exactly for a triangle-free drackn what happens with the spectrum, with one sort of small asterisk that I think I can remove. And so this is just setup. This is just the eigenvalues of the strongly of the drackn to begin with. And then I want to say, okay, well, what's going on with the spectrum of the subconstituent? And what it turns out is, well, you get some new valency, you get the eigenvalue you had before here, but the multiplicity drops a bit. Same thing with the other eigenvalue you had before. 0 shows up, this coefficient or this constant C2 shows up, and C2 minus 1 shows up. And the multiplicities are all determined as well, and all relatively nice to work out. And so I want to describe a bit of how that works this remaining time, and how we get this. The other thing I want to mention is, so this assumption that R is greater than 2, that's just to move out of that classical case that I described at the start. And the classical case, we're just getting these strongly regular graphs where these are, just 3 eigenvalues, because you're getting your second subconstituent is strongly regular, and you very explicitly know what those are in terms of these parameters. This case, it would be very nice if this also included C2 equal 1, because the C2 equal 1 drackns are going to be exactly those subconstituents of Moore graph that I described before. And the reason I had to do this when I was writing this up is I made my life easier by proving a combinatorial lemma, which is just that if I assume that C2 is greater than 1, I can always just show that this second subconstituent is connected. And then I know the multiplicity of the largest eigenvalue, and that makes things easier. And at the time, that was all I needed right then, and so that's what I used, and I just omitted this one case. It means we missed these 2 graphs, but actually, due to another result of Gardner, it's exactly these parameter sets we're missing, and they're the only triangle-free drackns with C2 equal 1 are the ones coming from the Moore graphs. So it's just these things being missed. And actually, this graph is small enough that you can check explicitly. And I did check, and actually the result holds for that as well. So really, it's just the only thing we don't know the spectrum of the second neighborhood of. I'll have that changed out so that this is a little bit tighter.
Could you go from the sentence about the second neighborhood, spectrum of second neighborhood?
Say that again.
Could you repeat what you said after the second neighborhoods of the subconstituents and the spectrum of those?
Yeah, well, I would like to be able to not use this combinatorial lemma and just go specifically from the linear algebra, and then also include this one last parameter set in my calculations. That's a sort of a piece of future work, but hopefully soon to be done future work, because I think I see how I can. I mean, maybe you'll see as we go through this how this works. Okay, so what's the setup of this proof that I want to talk about? And how are we going to actually work with these second subconstituents? And the idea, this is something Shirazi put forward, is that it makes sense to organize things in terms of these row and column partitions. So you look at the distance partition of this graph. We're specifically in a diameter 3 graph at this point. And what I've done now is I've taken the third piece and I've written it up top instead of over side, because, well, what's happening with this thing? So if I think about our coloring, right? Our coloring said, well, if this vertex X, this was colored red, and it's the first red vertex, then the other red vertices in this graph are all the vertices at distance 3 from that vertex. So there's these R2, R3, R4, say. And each of those has one of each other color in its neighborhood. So maybe there's and so we can always organize this. So these are the neighbors of R2, these are the neighbors of R3, and so on. So I can always sort my columns this way, or I guess it's sorting my rows this way so that my columns look like this. And that gives me this column partition, which is indexed by a vertex from V2. I guess I called them gamma here because this figure was from another talk, but gamma is equal to V for the sake of this talk. So I have a matrix indexed by these in the rows and these in the columns, which just records which column the vertex here belongs to. And then for this row partition, I do something similar, but okay, well, now what's going on with all of the neighbors of R1? Well, these neighbors, so this is maybe B1, the first blue vertex. Then the numbers are arbitrary, but the colors, they just have to be some complete disjoint thing, right? Maybe this is a yellow one, this is the pink one, this is the lilac one, I don't know. But the point being here that these things all belong to some fiber themselves, some color class. And so I can organize my rows so that these are all the other. So this is B2, B3, B4. This is Y2, Y3, Y4, etc. And I can always do these two things simultaneously because each vertex here has only one neighbor of each color. So I'm fine to make this organization this way. And this gives me these two matrices, which record something about the graph. And as we can actually see, going on to this next page, they give me a very explicit way to give a block decomposition of the adjacency matrices. And this block decomposition is exactly what you're getting by adding these projections into the adjacency algebra, which is sort of the moral of the Terwilliger algebra, or the definition of the Terwilliger algebra, the moral of the definition of the Terwilliger algebra. So what's going on here, I have this breakup into these things where I've got, so in the adjacency matrix, I've got these blocks, and I haven't told you the size of the block, but I'll just index them right now. This first block, this is just size 1, right? This is just corresponding to this vertex. This next block is size n-1, corresponding to these. This third block is size, well, the rest, but so this last block we'll go to first. This is size r-1, right? R is the size of the fiber, but we left out one vertex here. And then what's the size of this last block? Well, it's the rest, and you can calculate pretty easily that it's n-1 times r-1, right? And the same things in the columns as well. So this is this matrix B1, that's an n-1 by n-1 matrix. This is n-1 times r-1 by n-1 times r-1, etc. So you can get all the dimensions that way. And I'm leaving them off so that I don't have a million subscripts floating around. But so this J is just an all ones vector of length n-1. That one's just its transpose, etc. And the point here of doing these row about these row and column partitions is that they give us a way. They tell us exactly what to write here, and they also tell us what to write in the third adjacency matrix, or in the distance 3 matrix as well. Now the other point, I wrote this generally, but the other point here is that this B1, this is actually going to be 0 for triangle regular, if we're triangle free, because what is B0? It's the adjacency matrix of the stuff that lives inside this first subconstituent. So we actually have a 0, which is what makes some of our calculations actually give us something tight and give us a complete characterization of the spectrum. And then I should also mention this n. What is this n or this n transpose? That's describing the incidence between the second and third pieces. So just getting explicit about what we're looking at, because I'm about to start manipulating these matrices and they're going to be flying around, and it's good to have some grasp on what they are before we do that. Okay. Any questions about this setup? Okay. So from this setup, what do we do? Well, we now bring in one more thing we can bring in is that we can actually calculate the second distance matrix as well, just from the fact that it's a graph of diameter 3. I mean, it's just it's the complement of the union of the other two, right? If I take out the stuff, the adjacency matrix, I take out the stuff at distance 3, I take out the identity, all taken out of J, that's just giving me with the stuff at distance 2 matrix. So now we have all of these distance matrices, and we also go back to this fact that we know we're dealing with a distance regular graph, so we have the 3-term recurrence. And now we're going to be able to start using that 3-term recurrence to get a bunch of equations, but now we restrict our equation to the individual blocks. So for each I choose, so for each thing I multiply with the first adjacency matrix, say, and for each block, here, for each block here, I get some sort of sub-equation. And so in particular, I could look at the sub-equation for A1 squared 3, 4. And what would that be? Well, on the one hand, I go back to here, I look at 3 by 4 in A1 squared, right? That's the dot product in this block matrix sense of these columns. And that's just going to give me B2 times C, which is this. And then on the other hand, I can go to these individual matrices, look at and scale them by this parameter. And again, these parameters are known now. We've got these calculated from the parameters of distance regular graph and get exactly this, right? So that gives us this block equation, this sort of subconstituent equation, which actually is now going to give us exactly what we need to figure out some of the eigenvectors and eigenvalues of B2. Well, why is that? Well, I think I have that on this next slide, which is that if I have something that's orthogonal to the all-ones vector, but lives in the column space of C, then I'm going to explicitly get B2 CU, if U is that vector, is equal to negative C2U, right? Negative C2 CU. Right, so that CU is going to be an eigenvector with eigenvalue negative C2. And this column space, well, it's just a partition into R-1 disjoint pieces, and it sort of looks something like this. So, so it has dimension R-1. I pulled off this all ones piece. So I've got this eigenspace for negative C2 of multiplicity at least R-2. And we can figure out the multiplicity exactly once we're done with it, partitioning these eigenspaces up. And this still is already true just in general, that you'll have this sort of eigenspace with any drackn. I mean, I don't know how general that is, but without restricting to triangle-free drackns. But if we do restrict to triangle-free drackns, we can get more information from some of the other equations. And that's what I want to talk about next, which is, okay, this eigenvalue 0. I have an eigenvalue 0 with a certain specified multiplicity. Well, if I look at this equation here, this is the equation from looking at the 2, 3 block in this square of these matrices. That gives me this equation. But like I said, this is 0 because B1 is 0 in this context. And then, so now I have this simpler equation here, also this A1, that's counting the number of triangles on a vertex. So that's 0 as well. So this is a simpler equation here. And then I'll also throw in this other equation that comes from looking at A1, A3 from this product. And by putting these two equations together, I can see that in fact this B2 times N is equal to C2 times B2 times R. And so what does that tell us? Well, by subtracting something over to the side, that tells us that anything that lives in this in the column space of this matrix, this N minus C2 times R, that's in the 0 eigenspace. So that gives us some 0 eigenvectors as well. Now, we don't know the dimension exactly, but we know that anything that does live in that column space is going to give us a 0 eigenvalue. So we can do that. We can do that one more time as well, actually. We can do it with... we take the same equations again. Again, that's a 0. That's a 0. But now instead of we put them together in a slightly different way, and we get this sort of funny looking equation. But what that tells us is that anything which is orthogonal to J and lives in the column space of n plus r. So before we had n minus C2r, now we have n plus r. Well, that will be in this eigenspace. It's negative C2 minus 1 eigenspace. So again, we're getting more and more of the eigenvectors out of this. We sort of chop up the eigenspace more and more. Now is a good moment to stop and look at how we've chopped up the eigenspace thus far. We said, well, okay, there's the thing corresponding to the all ones vector. Then there's the things orthogonal to that, but that are in the column space of C. That gave us some of our eigenvalues. And then we had these two further partitions, one where we had the column space of n minus C2r, one where we had the column space of n plus r. And actually, if you're not in either of those spaces, we can sort of give a simpler description of the things that don't live in either of those spaces, because if you're in the kernel of the complement of those two spaces, then because C2 is greater than 0, these pieces cancel out, and you see that you actually had to live in the kernel of R transposes already. And because you had to live in the kernel of R transpose already, you also had to live in the kernel of N transpose. So sort of not being in any of these spaces, the upshot is not being in any of these spaces that we've already looked at means that you live sort of in the, you annihilate NT and RT already, if you're an eigenvector. And the reason I bring that up is that it's important when we look at this last equation, which starts off as this very ugly equation. This one is, I didn't write it down, but this one is from A1 squared to 3, sort of the belly of the beast. This is comparing the second subconstituent part right at the middle of where that subconstituent we're looking at is. And this starts off as a fairly ugly equation, but if I have any eigenvector for V2, which wasn't in one of those spaces that I already described the eigenvectors in, then it's going to be orthogonal to this bit, it's going to be orthogonal to this bit, to this bit, it's going to be orthogonal to this bit as well. So a bunch of what's up there falls away, and the eigenvector has to satisfy this equation. And because that's true, okay, well, now that means that the eigenvalues are just roots of this polynomial. And here's where I said you have to reach back all the way to the start of the talk, where I gave the explicit description of the eigenvalues of the drackn. The eigenvalues of the drackn, those theta and tau, those are just the roots of this polynomial. So what we've actually found out is, okay, well, what's left over, these are the things that persist and sort of stay the same eigenvalue. And so that gives us the last eigenvalue. So now we actually have, we actually have this full set of the eigenvalues.
It's near the end, so I see you're almost.
Yeah, I'm almost done. Yeah. So we have these eigenvalues here, and what do we need to do? The last thing to do is to calculate the multiplicities. Well, this multiplicity is 1. By our lemma, we proved, well, I didn't prove it, but I stated this lemma that I can show that this second subconstituent is connected. This one, at this point, this was the one that came from the column space of C. So that's R minus 2. At this point, we actually know that nothing else was giving us an eigenvalue of that, because we found where all the other eigenvalues go. And now we can bring in sort of one of our standard algebraic graph theory tricks of calculating the trace in two ways. We can use the trace to count walks of certain lengths on the one hand, or in this case, I guess they're counting walks. And on the other hand, give me sums of powers of the eigenvalues and set up a system of equations, which is now going to be a system of equations with 3 variables, the remaining multiplicities. Right, and so for this first equation, this is just saying the trace. We have a matrix with 0 diagonal. It's just going to be the sums of the eigenvalues counted with multiplicity. That's fine, and it's equal to 0 because it's matrix 0 diagonal. This one for counting the trace of b squared. We now square our eigenvalues, and now we have to now count edges. Again, 2 times the number of edges actually. We're getting them from each end. And then for the third one, well, we would be counting triangles, but we're dealing with a triangle-free drackn, so that our life is a little simpler there. And from this equation, or from this system of equations, we can actually solve it. That I won't show. It's a little bit grisly, but it can be done. And once you solve that system of equations, you get your remaining multiplicities, which I could just write in. This was n minus 2, n minus 2 as well. And then these two were the multiplicity from the drackn minus n minus r plus 3 and minus n m tau n minus r plus 3. So we actually have a full characterization there. And that's the end of the proof. Okay, and then I guess the only other thing I'll say is what are the next things to do? Well, one is, like I mentioned before, it'd be nice to say something of that putative parameter set, but is the only one that's missing. We know the spectrum now, but are we getting distance regular graphs? Generally, no. I mean, most of the examples I've seen, the diameter is low on these things, but it would be nice to have some understanding of the diameter of these graphs, probably using combinatorial methods. If we could push the diameter high enough, we now know we've got 6 eigenvalues. So if we can find examples with diameter 5 on the second constituent, then we'd be getting distance regular graphs. And just generally, we'd like to have more examples of drackns, in particular triangle-free drackns. That would be an interesting thing to work on as well. Those are, I mean, we can all, if you have questions about any of that, we can talk more about it as well. And I'll just finish with a picture of that 761 drackn. Thanks.
So the tool that you were using just now for partitioning things into rows and columns, what does it apply to again? To which graphs?
The rows and columns, that'll work with any drackn. So you need a drackn in order for that to be exactly what's going on. I mean, you can certainly get other sorts of partitions using rows and columns, but it's specifically the drackn structure that's giving you that row and column partition.
So, okay.
I mean, more generally, you can get a column partition anytime you have sort of a perfect code in your graph, right? You have a set of vertices whose neighborhoods partition the graph. Then you can get something like a column partition. The row partition, you're going to need something resembling an antipodal cover, or you're going to need some, like there's some other structure that you need as well there. And for those two to be complementary structures, you maybe need exactly a drackn. I don't know, maybe there's other situations where it comes up.